astrophysics and astronomy, of course, just to recapitulate that. I talked a lot about, like theoretical production of neutrinos, about neutrino spectra, about results in neutrino astronomy, just to recapitulate that, and also about neutrino from AGN, which was like a little bit more astrophysics inspired topic. Today, I just wanted to continue with another astrophysics inspired topic, like neutrinos from tidal disruption events. And at the end, I wanted to talk about cosmogenic neutrinos, because there are certain topics I don't have time to talk about. Like, for instance, you will notice if you look at the slides, there's a section on diffuse neutrino fluxes from active galactic nuclei. You can have a look at yourself if you wanted, and also like on neutrinos from sources connected to hydro energy cosmic rays, like following up what Annika was talking about on gamma ray bursts yesterday. But probably I will not be able to cover that today. So the first part today is on neutrinos from tidal disruption events. It's a little bit, like about what are tidal disruption events, about the story, and so on. So a tidal disruption event is an event where a star is getting very close to a supermassive black hole, and the supermassive black hole tears it apart, essentially, or takes it apart by tidal forces. We will come back to that in a second again. And then what you normally have is that an accretion disk would form from about half of the material of the star, as the other half is kind of like unbound, so it goes away. Okay, the half of it is like accreted towards the supermassive black hole, and then you have things ongoing, like you have like radiation shining. You may have even jets and other things which are happening there. So this is like what a tidal disruption event is, and it happens, as you can guess, quite frequently, but we don't have like precise information yet how often. Now, the focus was lost again because you started the recording. Okay. So there is some basics how to disrupt a star, actually. Once again, you need, of course, a supermassive black hole. And what happens is that if you look at the force which is exerted on an element in the star, on a mass element by gravitation, then you can also like balance that with the force exerted by the supermassive black hole. So SMBH stands for supermassive black hole. And this is like called or happening, or like if they're equal at a certain radius, which is called the tidal radius. In this tidal radius, where basically the force from the supermassive black hole would be big enough actually to rip apart the star, can be expressed in terms of the quantities, like the mass of the supermassive black hole, which is like the capital M, the radius of the star, and the mass of the star, which is the small m. And typically we relate the masses of stars to the masses of the sun, because so it's like a fraction of the solar mass, or some several times the solar mass. So you can see this tidal radius is of the order of 10 to the 13 centimeters for a solar mass star, and a star with a solar radius, and a supermassive black hole with a mass of 10 to the 6 solar masses. Now, there's one important thing with these tidal disruption events. They don't happen if the supermassive black hole is too massive. Because if it's too massive, what happens is that the star is actually swallowed as a whole, because this tidal radius is too small in a sense. It's below the Schwarzschild horizon. So that means the star is just approaching the supermassive black hole, and flop, it's gone. Okay, it's not disrupted, and there's nothing happening very much. And this leads to, let's say, an upper bound for the supermassive black hole mass, which is around 10 to the 7 solar masses. So it's a little bit uncertain, because it depends also on the radius of the star and so on. It's sometimes called the Hills mass, but it's around 10 to the 7 solar masses. So it's not surprising that most of these tidal disruption events are found in systems where the mass of the supermassive black hole is, let's say, between 10 to the 6 and 10 to the 7 solar masses. Because if it's too heavy, you cannot like disrupt the star. You would swallow it as a whole or suck it up as a whole. If it's too small, the luminosity is not high enough that you would probably not see very much, even though these also happen. Once again, a measure for the energetics is the Eddington luminosity. And in these systems, actually, you can already from comparing the energy you have in a star. If you think about the sun, remember that the sun is a few times 10 to the 54 ergs in terms of ergs energy. Like if you use E is even mc squared, you can translate it like that. And this energy needs to be reprocessed over a time scale of these events, which is of the order of a year, let's say. And from that, you can easily derive, if you compare that to the Eddington luminosity, that you have to be super Eddington at peaks. So that means typically these events are like events which are like explosions or disruptions or massive things which are exceeding the Eddington luminosity by a factor of 100 to 1,000 over a certain time span. So this is pretty interesting because it's like something which is really like cruel. Now, a little bit about TDE observation. So that now, first of all, is like astrophysics, if you want it. It doesn't connect directly to neutrinos. TDEs, I mean, here you have some of these names here, which are coming from a facility called the ZTF, the Zwicky Transient Facility. It's an experiment looking in the sky, looking for these transients. Transients is this kind of explosive events, and they find many of these tidal disruption events. And what you see here is the luminosity as a function of time, and the black body luminosity. This is kind of in the optical UV range. If you're an expert for wavelength bands, it looks like typically like this here. So you have like this rapid increase and then a decay, which is typically more or less like a t to the power of -5/3 decay, which is like coming from the theory of tidal disruption events. So this is why you would also believe that in many cases, this is a tidal disruption event. Could be also mixed up by a supernova in some cases. So there are some additional ingredients to that. But this is like normally how it would look like. Sometimes you also have like observations at higher energies, like in X-rays, but the X-ray observations are a little bit more puzzling. So for instance, in this case, you have a data point here. This dot is a data point, and here, these triangles here are upper limits, and then you suddenly have like high X-ray data again, then low X-ray data, some limits in between. So it's kind of, you know, like all over the place. Here you see you have low X-ray data in the beginning and high X-ray data at the end, which is maybe not what you would expect from the black body luminosity evolution here. Here you have sort of like an exponential decay of the X-rays and then upper limits later. And here you have like upper limits, but there are actually measurements in between. So this is something which is like very non-uniform and also a little bit disputed, like how to interpret this X-ray data. And there's also radio observations, like in about, I should also say that these X-rays are not observed in all cases, only like in about, let's say, 1/4 of all TDEs. And the same for radio signals. You find radio signals in about 1/3 of all cases. And typically, some of these are more luminous, which are associated with relativistic jets, especially if they're kind of like evolving in time. And others are less luminous, which are probably associated with non-relativistic outflows. And in between, there's some kind of transition zone. You can see, for instance, this one here like is somewhere in the middle between these two different regions. But that's just like a summary of observations, but it does not have anything to do with neutrinos yet. So just to give you like a theory cartoon picture how these events look like, you typically have, after the disruption of the star, the formation of a disk which circles around the supermassive black hole. The debris stream is essentially the incoming material in this plane, or the infalling material. And then you would produce, like through reprocessing material through the supermassive black hole, outflows, which are at different speeds in different directions. Typically, it's a little bit faster in this direction and slower in that direction. And you may have also like a jet, which then clears this funnel here. So that is like in this direction, like perpendicular to the actual like plane where you would accrete the material. The jet could evolve, not in all cases. It depends a bit on the spin of the supermassive black hole. But there could be like probably better visibility if you wanted in this direction. That's what's called funnel. And the idea here is that the X-ray data depend very much on in which direction you look at to the event. So if you look in this direction here, you wouldn't see the X-rays, which are probably coming from some of the inner regions of this event here. But if you look into the funnel, you may see the X-rays because it's kind of cleared here. So that's why we probably see X-rays only in some cases, and why they are fluctuating, because if you picture that this material is actually non-uniform and there are like three-dimensional effects and whatever, then it could easily picture that the obscuration may be like causing this kind of fluctuations. So this is actually like coming from simulations, like relativistic MHD simulations. Now, let's come to the neutrino observations. So neutrinos were actually observed first for the tidal disruption event 2019 DSG. So this was an observation which was published, let's say, by a part of the IceCube collaboration, not the full collaboration, together with the ZTF collaboration. That's like a follow-up study. And so they looked at different events, and they found an association of a neutrino which actually came of the order of like 180 days after this zero here. So it's a little bit tricky sometimes, because sometimes the zero is at the peak time. Here the zero is when the observation started. The peak of the TDE is actually here. That's about half year after the peak. This is where the neutrino was observed here. So when actually the light curve already kind of decayed here. You see also the observations in like the ultraviolet range, which are like these different ranges here, and UGR GR are at least like optical wavelength bands here. So you see, oh, they're maybe like a little bit different, but this is also depends on like what kind of like energy window you're taking. So don't take this too seriously, this difference. You really have to work out the overall luminosity. But you see this kind of decay, you see the late time neutrino. In this case, you also had like actually an X-ray signal. So the X-ray signal seems to be kind of exponentially decaying, because this is like a log linear plot, and lines in log linear plots are exponential decays if you work it out. It's not like a power law, which you have like in log plots. So you can think about that maybe at some point, and then you would see that this is like exponential. And then there are upper limits later. At the neutrino signal, there was no X-ray signal, as you can see here. The X-ray temperature was about 60 eV. And there was also like an evolving radio signal, and evolving radio signals, as I said, they can be interpreted like as jets, for instance, or maybe outflows or something like that. So that was interesting per se, and you can do a lot of interpretation. For instance, we also had a model like on a jetted model where you would have a jet producing the neutrino, which at that time was like something which you probably couldn't exclude, because there was this radio signal. But then, I mean, more insight came actually also later with other events. So there was actually a little bit later another observation, not too far away in time, when you see here like the optical luminosity here in green, which also looks again like a typical TDE. It's actually a little bit longer, like it has like a year time scale. Here the neutrino was coming at that time, about a year after the peak, okay? And the interesting thing, which they realized there, that there was a so-called like dust echo. So dust echo means that if you look at the system here, where you have probably the black hole, maybe a jet, the disk, a corona around the disk, and the streams here, that material or like radiation, which is like produced in the inner parts here, is kind of reflected and reprocessed in dust surrounding the system. So that means that high energy radiation is reprocessed, and it exits at lower energies, like in the infrared range. So you would reprocess like black body, optical UV, maybe even X-ray radiation into the infrared. And of course, I mean, this doesn't only happen like in this direction. You could also have dust down there. So you would have like material or like a radiation running in this direction and then coming back towards the observer. So the size of the system here, which is in this case of the order of 10 to the 17 centimeters, that's of the order of 0.1 parsec, would be indicative like for how large the size of the dust system is. And this kind of like size of the system would cause this kind of like delay, which is illustrated here, where you have like the dust echo as these kind of like diamonds here, and the fit to it, which is like this curve here. And you see it's basically like a delayed radiation from the black body here, which shows up later. And it's interesting because it peaks sort of like where the neutrino peaks. And the question is that a coincidence? Here you also see the fits in 3 different like time bins, if you wanted. So it's like a double black body fit where you have the optical UV here, which is like this one here, dominating at high energies, and a small dust signal. Later, the dust echo here would actually dominate, and here also at that time the dust echo dominates. So that's interesting, because now, I mean, first of all, you have a second event where the neutrino came of the order of, let's say, half a year after the peak, okay? Second of all, as I said already, like on Monday, I mean, these TDEs are interesting because they have a relatively interesting balance between luminosity and distance. So the redshifts are not too high so that you wouldn't see anything for these kind of luminosities. They're sitting kind of like in the sweet spot. And you have this commonality of like a dust echo. In fact, this TDE was also observed like in X-rays. That was not so much interesting in the radio. Now, once they realized that, okay, fine, now we have like actually a second TDE, and they realized, oh, the first one also had a dust echo, which was not realized in the beginning. So what they did is, or some people did, like von Felsen et al., they said, okay, let's do an analysis and look specifically for signals in our ZTF data sample which have a dust echo. Okay. And they actually found by that another neutrino candidate. And this third candidate is called AT2019 ALK. So you see here in these three different panels, the luminosity of the black body compared to the dust echo, which is like a delayed here. Here, this is for AT2019 ALK, where you see also the strong dust echo coming later. Here, this normalization is larger than that, but as I said, that's a little bit misleading because it depends on what energy band you're actually looking into. Maybe this is more illustrative, where you see the neutrino signals here in the same colors as the like black body signals. And you see also in the third case, which is the green case, it was like of the order of like half a year after the peak. So there seems to be some kind of like pattern emerging there. So it's not like, you know, this is something which is like a lonesome signal. So if you wanted to think about what that means now, it means what do these events have in common? That's what I would ask. And the common features of these three events are that they are detected in X-rays. The X-rays signals, on the other hand, are qualitatively very different. They have very large blackbody luminosities, and of course, there are strong dust echoes in the infrared range. And the neutrinos are all delayed with respect to the peak by the order of 100 days. And in fact, the neutrinos, as it's illustrated here, they all come at sort of like the peak of the dust echo. So that's something you can look for in the future, and maybe you'll find additional events which look like that. So far, the overall significance is not so high. And there are some kind of discussions about, you know, like if you improve the directional information, maybe some of these will move out of the error center. But I just try to convince you that there is not only, you know, like, oh, I do some kind of analysis of correlations of directions and so on, or timing here, but there's actually a story behind that. Okay. Now, the question is, where are the protons then accelerated if you produce neutrinos? I mean, you can picture about different acceleration sites. For instance, you may have like a jet, which may not necessarily have to be pointing towards the observer. It could be also like off axis or in a different direction. For instance, if the protons are leaving the jet, they could be isotropized in a colorimeter if you have like magnetic fields here in this system, and then they would interact somewhere. You could have like a particle acceleration in the innermost parts, like in the core, similar to what we have in AGN core models. So that also has been proposed. Or you may have like particle acceleration in wind-wind collisions, or when the outflow hits the circumburst medium or the circum-TDE medium. That's also typical models which are similar to like supernova models. But we don't know precisely where the particles would be accelerated, and there are different kind of like options. I think the thing which is probably fair to say is that I think at least that the accelerator is kind of TDE particular. That means you would find it in this kind of systems, but it's probably not the same kind of accelerator you have in other systems like AGN cores, because otherwise you have the problem that you have to explain why the AGN neutrinos don't outshine these neutrinos by a correspondingly large factor, because AGN overall are much more luminous. So it's like a problem which you need to open then if you postulate that the accelerator is very similar to like AGN. Okay, so what we actually are interested in, just to come back to that, like also what I was trying to emphasize on Tuesday, for the neutrino production, the acceleration is of course very relevant because it's like the most important thing we would like to test. But even more relevant is like where do actually the interactions happen? And for that, we can also look at the different radiation fields we have available here and what that means in terms of the proton energy. So this is just a summary of the properties of these three TDEs, where you see also the black body temperatures in EV. So that's like in the optical range, it's like order EV. In X-rays, you have of the order of 100 EV, and in the dust echo, you have of the order of like 0.1 EV. So that's in the infrared range. And if you go back to like the slides from Monday, you can also like relate that again to the target photon energy you need for the interaction. Remember, we had this relationship between target photons and protons, or like neutrinos. If I produce a PeV neutrino, I need like, let's say, if the Lorentz factor of the system is 1, it was like order 10 EV target photons. And this is recasted here in these formulas in terms of the temperature of the target photon field, because now here we have like a black body spectrum, not like a power law spectrum. And you see, you can translate this into like a requirement for the maximal proton energy, which is 20 times the neutrino energy, which depends on the target photon temperature. And if you look at the different target photon fields which you have available, like the optical, the X-rays, and the infrared, that translates into certain minimal required proton energies. And if you look for, if you, for instance, wanted to go for interactions with the X-rays, that's the one, in my view, very interesting, because you need very low maximal proton energy. So that means you have relatively moderate requirements for the accelerator. Coming from this formula, you need about 2 PeV protons. If, on the other hand, as you know, like the association actually suggests, because it's like time correlated with the infrared signal, you want to have the dust echo as a target, you need like proton energies beyond like 1 EeV, like 10 to the 18 EV. So that would be like ultra high energy cosmic rays, a connection to the cosmic rays at the highest energies. I will come back to a little bit later in a different context. So in a way, the photon field controls the maximal proton energy needed, or vice versa. And you can think about, you know, like where in the system you would best do these interactions and accelerate these protons, like from that perspective. So that's like a more abstract level of how to find the accelerator. If you wanted then to relate this to how efficient does my acceleration have to be. I don't want to enter a lot of further details. I just want to keep it qualitative at this point. There are other aspects in this game. For instance, what is the origin of the neutrino time delay? So if you really believe it's correlated with the dust echo, then you may think that maybe the target photons, like the infrared photons, they indeed build up with time. So that would require ultra high energy cosmic rays interacting. Remember that? And that's apparently like related to the size of the newly formed system. So the dust echo would be like, of course, a very good target because it explains this time delay. But you could also think about options that the accelerator appears delayed. For instance, you have some kind of transition in the accretion disk state. There's some impact of the circularization time or something like that. Or you could have something which is a little bit more complicated in the first glance, but we haven't talked about yet. You could have like a colorimetric behavior. So that is, you don't actually have efficient interactions of the scale over the system, but you actually confine the protons over a certain time in the system. And you can come back to what actually Enrico was talking about, like the, let's say this is a different recast of the diffusion. If you have a diffusion coefficient T and a certain time available for diffusion, then you can displace particles by a certain distance, which I called R here, okay? And if you were like recast that in terms of the parameters, it turns out that over the 1000 days, the system lasts for a Gauss scale magnetic field and a PeV proton, you can get as far as like, let's say 10 to the 15 centimeters. So if you have a system, like let's say a radiation zone, which is about 10 to the 15 or 10 to the 16 centimeters large, that means that only protons higher than PeV would escape, and everything at lower energies would be confined, and they would not be able to escape over this time scale, and they would interact like delayed if you wanted. And that's what's illustrated here. I haven't shown many of these figures in these lectures. Normally, if I do longer lectures, we discuss this in greater details. But if you look at the interaction rate here on the vertical axis as a function of energy, you see that there are certain like straight lines here which are related to the size of the system. So that's TFS is the free streaming rate, whereas you have here the dynamical timescale of the system. So that's like this 1000 days if you wanted. And you see also the escape, let's say, of protons illustrated here, which is the red curve. So you would have like magnetic confinement up to a certain energy, and they just like the Lama radius reaches the size of the system, and then you can escape, okay? like, of course. So that's like would be the proton escape. And if you look at this interaction rate here, that's a P gamma interaction rate, you see it's like smaller than the free streaming rate. So that means the system is actually optically thin, but it's higher than the escape rate of the proton. So that means it's colorimetric. So that means the proton can interact over the dynamical timescale of the system, but not like over the just like free streaming propagation time. Like if you were not deflected, like a neutron, for instance, a neutron is not magnetically confined because it's not charged. And this leads to effects like, which is illustrated here. If you, for instance, inject the protons with a luminosity which follows the black body luminosity of the TDE, then you would accumulate protons over time, which is illustrated by the dashed dotted curve, which would correspond to the in-source density n, if you recall that from Monday. So that would like basically accumulate and then would decay very slowly because it's like driven by this kind of like P gamma interactions, this decay. And you get also a delay here for the interactions. It's not following the initial injection, but it follows this colorimetric behavior. And you have truly time-dependent systems, which you have to simulate there. I just want to show you at the end of this part, like one example where you see this time-dependent behavior. So that's like for AT 2019 FDR, that's one of these TDEs, where you see the black body luminosity evolution. You see the neutrino signal in this case. So it's driven by the dust echo, in fact. This is this purple curve. It peaks sort of like at the time you would have actually observed the neutrino, but it's not like uniquely peaking there, could also be coming earlier or later. You also see what we have been talking about a lot is the electromagnetic cascade. So remember, if I inject neutrinos here in the spectrum at this level, I will also inject the photons at this level, and they have to show up somewhere. And here they actually show up in this energy range because you have attenuation here by gamma-gamma interactions. So that is like at this point, this cutoff is coming from the interactions with the X-ray photons, which we know that we have them in the system. So you see, you have comparable amounts of energy, but they would show up here at lower energies, like in the GeV range. And you have a signal which looks like the neutrino signal, which is like the hadronic electromagnetic, let's say, the electromagnetic cascade driven by the hadronic parts, so which you see here in this case. So that's like in this case perfectly accommodable with bounds also. So that's not the issue, but it's showing that you could also search for this kind of like correlations in a different way by looking for gamma ray signals which are correlated with the neutrino signals, for instance. So it just shows you what's going into that. But what you can infer from that is also that the event rate per TDE cannot be or must not be too high, because if it's too high, you would also produce like gamma rays efficiently, and that would run into like problems with the bounds which we have from Fermilab and so on. So I would hope that at some point we see something also in the gamma ray instruments which would be correlated with the neutrino signal, because otherwise, I mean, it's difficult to explain that probably in most models. Let's put it like that. If you don't see anything in any wavelength band, we had this discussion, then where should the electromagnetic cascade coming with the neutrinos actually go to? I mean, this is always the question. Okay, so much about like the tidal disruption events. I wanted in the third lecture actually establish a connection with the ultra high energy cosmic rays, and I will probably only be able to cover a certain part of that. That is the cosmogenic neutrinos. But before that, maybe you have seen this figure already before. I think it was shown in one of the talks so far, which motivates that. So where you see as a function of energy, the signals we have in gamma rays, neutrinos, and cosmic rays. And this is E squared times the flux again. And you see they're all at kind of the same level. There are some strange features here, like for gamma rays and cosmic rays, like this kind of like cutoff and this kind of, also cutoff here. But this is some effects we understand. They come from the transport of these particles. So at the end, the energy budget is kind of the same if the neutrinos really have like e to the power of -2 spectra. So that motivates, of course, people to think about, is there a connection maybe to these gamma rays, as I showed you in one of the figures from Marcus's papers, or like maybe to the cosmic rays on the other hand. So for that, I mean, again, before I talked about astrophysics of TDEs and then about neutrinos, now I will talk about ultra energy cosmic rays actually before I talk about neutrinos. So it's again a little bit different subject. So what do we know about cosmic rays? Cosmic rays have been measured like over many decades in energy. This is one of these pictures where you see e to the power of 2.6 times the n over dE. some strange units. They like to power this spectrum by units of e to the power of something to make it look flat. And then you would also be able to identify certain features, which you can call knee, second knee, or ankle, perhaps. If you talk about ultra high energy cosmic rays, it's typically this range beyond like 10 to the 18 eV or 10 to the 9 GeV here. So that's the highest particles we have ever observed in the universe. And that's, of course, very interesting. There are other observables I will come to in a second. For instance, this is the average of the mass number. A is the mass number. So it's average ln A. And I find this figure illustrative because as a function of energy, it shows you that apparently these particles seem to be getting heavier and then lighter again and then heavier again. And that is something which is related to what we believe is a so-called Peters cycle. So in the beginning, I also showed you if I balance the centrifugal force with the Lorentz force, I get a maximal energy which scales with the charge of the particle. So E max is proportional to Z. So if you believe that this is implemented in the sources, you would have like an increase with energy of the composition, which is proportional to charge, or this is also proportional to the mass number of the particles. And then such a drop could be easily interpreted as a transition to a different population of sources, like perhaps the galactic extragalactic transition. And then here you have an increase again, which corresponds to one of these Peters cycles. So that's the standard, like I would say, typical or like the most primitive interpretation you can have of this kind of thing. So we are talking about different populations here, which are getting heavier and heavier at higher energies. The experiments we actually use to measure these particles are ultra-high energy cosmic ray observatories like the Pierre Auger Observatory in South America, in the Pampa, or the TA, the telescope array experiment in Utah, where you see Salt Lake City here. So you can picture these as an array of detectors on the ground, like these here, plus several like fluorescence detectors. That's like, let's say, telescopes which look into the sky for like light produced in the atmosphere. Okay. And by the combination of these, you learn something about these particle showers, which are created by the interactions of the ultra energy cosmic rays in the atmosphere, which develop there, have certain like contents, which like electromagnetic and hadronic contents. And you try to measure these let's say properties of these like showers, which yield in observables, which are the spectrum of the particles, and two observables related to the composition. So this is like sometimes called average X max and sigma X max. So that's also properties related to the height and the spread of the air shower. And these can be translated then into the mass of the particles if you know your interaction model, like your particle physics interaction model. So at the end, if you like translate all these data, what we typically look at in, let's say, phenomenology are these observables, as I will show you on the next slide. So that's like a typical of these figures, which you will see like many different times if you do this kind of like science, where you have like the spectrum here, that's like E cubed times the spectrum actually. The data points here are these bullets here. You see there's some uncertainty like showing up at higher energies. There are different contributions of different populations here in different colors. These colors seem arbitrary, but they're typically the same in all of these figures because they're related to certain mass groups. That's like, let's say, the PAO, the Pierre Auger Observatory corporate identity colors. In red, gray, green, and blue, different mass groups range from like hydrogen, helium, nitrogen, and iron. That means you don't like look at individual isotopes, but you summarize all of them in a certain range into different mass groups. And depending on the mass, these observables like these, let's say, height of the air shower and the spread of the air shower, the hadronic components, they will vary as a function of energy. And you can interpret like this, like as getting a heavier composition at higher energies here. And this is like expressed here also in different contributions, which would contribute here. The blue one would correspond to the iron group, the green one to the nitrogen group, and the gray one to the helium group, for instance. Now, this is like what you normally see, these three. I added another one because the interpretation of this X max and sigma X max is actually not so easy. So what does it mean here? It looks like it's getting all heavier at heavier energies. But in order to see what's actually happening, it's maybe more useful to look at this so-called umbrella plot. where you subtract the X max for iron here, or the sigma X max, which is the lower value, to get rid of this like shape here. And then you will plot X max versus sigma X max, the measured values, like here as this crosses here. And if you compare that then to like models where you have like a transition, let's say from pure hydrogen to pure iron, you would be living along this line here actually. Whereas if you have like a mixture between hydrogen and iron, which you could also picture from these figures maybe, you would deviate from this line. So what this tells you is, that is a little bit of dependence on the interaction model as well, but what this kind of umbrella plot tells you is that the way to interpret these observables is like you have a transition essentially from pure hydrogen at lower energies to pure iron at the highest energies, not like some kind of mixtures of isotopes or elements, which you would like naively also be thinking it's possible. And that's also expressed here by these different very hard components here. So that's like just like an add-on for the experts among you, but you can also forget about that again if you think it's not relevant. What's more relevant for us, it's in fact ultra-high energy cosmic ray transport. If you wanted to talk about cosmogenic neutrinos, we have to understand how these cosmic rays are transported from the source to the detector. And I come back to my cartoon picture I showed in the very beginning, where I had my astrophysical source and the different messengers. I just wanted to illustrate here that these transport models, they enter actually at the, let's say, at the interface between the sources and the circumsource or the intergalactic medium. So that means propagation models typically don't care what happens in the source, but instead you would describe what's ejected from the source or escapes from the source in terms of like typically ingredients which are a power law injection spectrum. Injection is misleading in this sense because we are injecting into whatever the extragalactic medium, but it's actually an ejection spectrum from this point of view of the sources. So that leads sometimes to confusion because the power law spectral indices, which we'll find later, may not be necessarily like e to the power of -2, which you have like from Fermi shock acceleration, but what you escapes from the source. Typically, another ingredient is the composition, of course, and the maximal energy of the different isotopes. And the simplest relationship between maximal energy and composition would be that you would assume that the maximal energy follows a so-called Peters cycle. So that means it's case with the charge of the particle, as we will see. And you have to distribute your sources somehow in the universe. So typically, you would parameterize that by like a source evolution, which follows like 1 plus redshift to the power of a parameter called, let's say, m. We will see later why this makes sense. I mean, even though like the star formation rate evolution is actually a little bit more complicated, but since ultra-energy cosmic rays don't travel very far, we just need to parameterize the part which is very close to us, you know, like up to a redshift of 1, and that's very well described by this kind of parameterization. Then if these particles propagate then from their sources, they will be like interacting. In fact, the main interaction is like nuclear disintegration of nuclei, plus photohadronic interactions like this one here. The proton, for instance, will produce like on the cosmic microwave background, which is filling the whole universe, like the delta resonance, and would produce neutrinos as well. And there's a number of different transport codes which you can use, which can do this simulation for you. Many of these are public, like SIA proper is probably the most famous one, but also others like Prince are published codes. SimProp, I think, is one of the ones which is also popular and so on. So these codes would do this transport for you and also compute the cosmogenic and the cosmic neutrino and also gamma ray fluxes. Okay, so the transport of ultra-energy cosmic rays can be described by equations again. The equations are in fact not so different from the ones I showed you earlier, like on Monday, where I described the source itself, like where we had this radiation model, where we had like, you know, describing each species described by one of these equations. Here, I don't have like a quantity which we had like in that case, which was called N. If you remember, N was the in-source density, but it's like Y, which is in principle the same, but it's divided by the cosmological filling factor. So it's like N divided by a to the power of 3. So you divide out the expansion of the universe there. So probably, I don't know if you talked about this already this morning or in the cosmology lecture, but it's a typical, I saw it in the exercises, these kind of games, typical way to like reparameterize the problem that you don't have to worry about that. And also, I mean, it's a little bit more simple from the point of view of the radiation processes, because the radiation processes happening there are well understood and are certain specific ones. We don't have like all sorts of like cooling and whatever Bethe-Heitler pair production and other things going on. But we know that we have adiabatic losses because of the expansion of the universe. We also have pair production losses by Bethe-Heitler pair. So it's not true that it's not going on, but this is maybe a bad example I used, but there are other processes which are not happening. Bethe-Heitler pair production is happening here. And we have interactions by like, let's say, you interact with the CMB, or like you have disintegration where you would like escape into a different species. Plus you have injection like from interactions or from the sources. So it's like a particular set of radiation processes. Like in the sources, it can be a little bit more like complicated because you have more different things which could be happening there. Here, these processes have been relatively well studied and also like related to the cosmic microwave background. And in fact, like the extragalactic background light beyond that. And this is illustrated here where you have as a function of wavelength or photon energy, the different target photon spectra and number of particles per cubic centimeter is a function of energy. There you have the cosmic microwave background, which is our main target here, which fills the whole universe, as you know. But there's also like a background from like stars and all sorts of other processes at higher energies. You see this would be like this red curve here you could interact with. A complication, of course, is for these kind of backgrounds, the further I look back, the higher they actually are, and also the higher they are in energy, because they are cosmologically redshifted. So if I propagate my particles, they will, in the earlier universe, experience higher interaction rates. And that's illustrated here, where you have it for a redshift of 2, for instance, and there is a dotted curve, so the normalization is higher and the peak energies are higher. And you have to take into account these effects. So it's not sufficient to just look what happens in the local universe. And here I just show one example for one of these particles that would be nitrogen ions, where you have the energy loss length here. Before I showed the interaction rate, which is the reverse. For the energy loss length, it's always like the lowest one wins. So that's like driving the process, the driving process is a function of energy. And you see the typical or one which is driving this game is photo disintegration. So that means nitrogen will interact with like the CMB photons, which will make it fall apart. So like, for instance, you may split off light nucleons. That's the typical process here. And you see at higher energies, that's the main process, but you could have also photohadronic interactions, which is the orange one, and that would lead to the neutrino production actually. So that's interesting for that. Plus you have the pair production in blue here. You again have the complication that it depends on the redshift. I mean, if the redshift is higher, the rates will be also higher, or the energy loss lengths will be lower here. So that's by the lower ends of the shaded regions. So the interesting part is, first of all, we have disintegration dominating the game. We do have like a contribution of photohadronic interactions at the highest energies, which will produce our neutrinos. But what's also interesting is if you look at this length scale and you compare it to redshift 1 would be roughly here. You see that these particles actually, they're not traveling further than like redshift 1, because they would be cooling, in this case by adiabatic cooling, or at higher energies they would disintegrate. So that means for cosmic rays, we cannot see very, very far. And that also means that if this is something you should always remember, whenever we talk about cosmic ray data fits, they will only tell us something about neutrino production up to a redshift of 1. Beyond that, only neutrinos can tell us what actually happens. And this is also like an interesting test bed for, like, let's say, high redshift cosmology. I'll come back to that, but before that, I want to discuss what happens for like protons. And that's actually a number of figures from Maurizio, like relatively early figures, but I think they're still quite illustrative because it's like the old paradigm, let's say. If you have protons only, you have like as a function of energy a certain behavior which you can produce, which actually reproduces data in the spectrum very, very, very well. And this kind of behavior is produced by particle physics processes on the cosmic microwave background only. Namely, you have like a dip here produced by pair production, and then you have like a cutoff, like it's actually also like a spectral break. It's not a cutoff, which comes from the interactions with the CMB photons. It's proton plus CMB photons, sometimes also called the GCK cutoff. This is something which you also see in the energy loss length here as a function of energy for the protons. I think it's easiest if you look at the redshift of 0 here, where you see at the highest energies, this is like you have P gamma interactions, which will be driving the game. And here at lower energies, you have the Bethe-Heitler pair production. So this kind of shape here will translate into that shape. And then this kind of like transition here would translate into this cutoff. So that's like a little bit crowded maybe, but these features can be explained by that. Now let's take a look at the neutrinos. What does it mean for the neutrinos? So for the neutrinos in this kind of model, they typically will produce a peak of neutrinos at about 10 to the 9 GeV from interactions with the cosmic microwave background. So that's this red curve here. But I also showed you earlier that you have other background lights, like infrared backgrounds, backgrounds from stars and so on, that will produce like the blue neutrino signal here. Plus, there may be like neutron decays, which could contribute at lower energies. Now, it's interesting to think about what redshift slices contribute to that in these cosmogenic neutrinos. And here in this figure, you see that, in fact, also the high redshift parts, which are like the thicker curves here, they would contribute substantially. So that means you cannot just say, okay, I look at like low redshifts, which are relevant for the cosmic rays. Remember that any cosmic ray data will only be sensitive to redshifts up to redshift 1. But the neutrinos, for them, it's actually important, these contributions, and they would add up to the total neutrino signal. You could also think about playing with the spectral index. And if you make it very soft, the spectrum here, you can in fact also have like a substantial contribution to PeV neutrinos. Remember, this is only for protons. So protons, of course, as ultra energy cosmic rays, like pure protons, have been excluded. So it's like just illustrative at this point. And this can be excluded, can be also quantified. So if you fit your cosmic ray data, this is like a fit at 1, 2, and 3 sigma, marginalized over all possible parameters. You can describe, for instance, telescope array data in the pure proton case very, very well. So this would be like a composition which consists of protons only. But if you like compute the neutrino data corresponding to these regions, they would violate the IceCube data already like quite some years ago. So that means you cannot have like protons only, which you would also see from neutrino data alone. Even if you don't look at the Pierre Rocher data. So there are like different arguments why this cannot happen. Also, you can look at gamma rays, would give you like similar results. So what do we do like in the future to learn more about that? There are certain experiment classes like GRANT, for instance, that's called Giant Radio Array for Neutrino Detection. The cosmic rays would interact in the atmosphere, produce a shower, which you could detect by radio detectors, which is really an ambitious project, which is going to happen perhaps in China. This radio emission comes from 2 processes. One is basically a separation of charge in the geomagnetic field, which would lead to radio signals. One is called the Askaryan emission effect, where at the shower front, you would have like a separation of charge, and that would also contribute to your radio signal. And they do this in a kind of like different way regarding the polarization. So if you're interested in the details, then I would like look at this reference, for instance. There's like a little bit more detailed discussion of that, because it's not so easy to explain. In fact, most people try to, you know, like escape from this explanations. There are other experiments as well, like for instance, this is like RNOG. It's a prototyping experiment in Greenland, which could also be like a prototype for serving for like IceCube Gen 2, where there's also a giant radio array planned. And this is like just showing you some examples how this is done. For instance, here you have like a box which is heated so that you could sit in your comfortable box and drill some holes in the ice, and you have nice and cozy like atmosphere, I guess. But as a theorist, it's difficult to, you know, like to actually judge that. But it's interesting science. That's one of our PhD students actually doing that. Now, the question is, what does it mean now for like nuclei, and how does it relate to these future experiments, like all this whole game? And for that, I come back to my transport model, which is, let's say, the state-of-the-art transport model for the nuclei, where we inject like this power law spectra from the sources with a spectral index of gamma. we would have like as a parameter the maximum rigidity and would postulate that the maximal energy follows that. So it's proportional to Z times the maximal rigidity. We would have source evolution with like 1 plus C to the power of M, where M is about 3.4 for star formation rate evolution. And you have 3 injection fractions for 5 different mass groups. And you would see that this is like the best fit at higher energies, like in this model, for instance, to the Auger 2017 data, for the spectrum, for the composition Xmax and sigma Xmax. So it nearly fits like perfectly. And you can think about what it means in terms of the parameters. So these are like the projections on the parameters. It's maybe not so interesting to look into all of them, but the most interesting part is perhaps this here, where you see the spectral index. Remember, this is e to the power of minus gamma. So 2 here is the Fermi shock acceleration spectrum you would expect, and the source evolution. And one thing you notice here is that you have some kind of degeneracy between source evolution and spectral index. So you can either have like sources which are like softer. Softer means like in this case sitting here, and they're like nearby, because -6 would be like nearby sources. Or you have sources which are harder, but they're by the attenuated by the propagation, and they're further away. So there's some kind of degeneracy along this curve here. So either you have something like star formation rate evolution of sources like GRBs, AGNs, or something like that, but they typically require a relatively peaky spectrum. So -1 would be basically a monochromatic ejection spectrum from the sources, something which could be driven by like diffusion, or like what we saw also in Enrico's talk. You have like actually in some of these models proposed a bell-shaped escape or something like this. Or you have like rather Fermi shock acceleration spectra, but they would need to have negative source evolution. And a source class, which I mentioned like earlier, but I didn't discuss in this context yet, which has negative source evolution, most probably because the supermassive black holes show up like more like in the current universe than earlier, are tidal disruption events, in fact, just coming back to that. Negative source evolution means that there are many more sources like at redshift 0, like now, than in the earlier universe. And for the black holes, that's probably a natural assumption. I mean, we don't really understand how black hole formation for the supermassive black holes apparently work. But like for lighter black holes, for instance, you know that black holes tend to like merge, and then you get more massive black holes. Okay, and this of course like happens over time. Yeah. Okay, that was just a short detour. So what does it mean for the neutrinos now? You can try to post-dict now from these cosmic ray fits the neutrino fluxes. And the problem is, as I said before, is that we don't know from the cosmic ray data, like from this data, what happens beyond the redshift of 1. So we can only speculate. So if you produce the neutrino fluxes, that would be like the 3 sigma allowed regions from the fit. Then you have to make certain assumptions about above a redshift of 1. Either, if, for instance, it continues as it was below a redshift of 1, that would be the orange curve. Then you could have like a relatively high neutrino signal, or you assume like flat source evolution, or there's no injection at all. But at the end, I mean, whatever you do, if you compare to one of these future experiments here, you don't see anything. So that's what cosmic ray data actually tell you in this model. The same if you do like different source evolutions. Whatever you do, you don't see anything. And that's like kind of the baseline fit, where you have the peak from this cosmic microwave background and the EBL interactions. So that means if you go for the baseline Peter cycle cosmic ray, ultra energy cosmic ray fit model, I don't think that you would see any cosmogenic neutrinos. Cosmogenic neutrinos would come from like light elements, which you would like inject in addition to that. And that's just illustrated here. Like this is a combined fit, a relatively recent paper, where we looked like how much light element injection you can have in addition to like these heavy elements. What you see here in the background is this kind of Peter cycle model, which would describe the ultra energy cosmic ray data at the highest energies here again. And on top of that, you have an additional contribution, which is actually like this proton dip model, which I showed you before. It's subleading in cosmic rays, so it doesn't screw up your cosmic ray fit here. But in fact, it's leading in neutrinos. So it would actually dominate your neutrino fluxes. That's the brown region at the highest energies. So mix here is the cosmogenic neutrino flux from this like Peter cycle model. And the brown region is the cosmogenic neutrino flux from your subleading, let's say, proton dip model. So you can have high neutrino fluxes, and we also do see that in certain models if we like combine it with the source model. In these baseline fits, like where you only assume the minimal ingredients to describe ultra energy cosmic ray data, they will not show up. So there's large uncertainty in that. So it would be major discovery, because actually conversely, we can learn something about these additional contributions from the like ultra energy cosmic ray interaction neutrinos, the cosmogenic neutrinos. But from my point of view, I'm not sure if, like at the highest energies, this is actually the dominant signal. Could be also that we find sources there like AGN, which are actually dominating the signal. For the protons, it's kind of similar to the proton dip model, because you have to have like this kind of 2.7 or so, I think, but I have to check it. Like, yeah, the heavy nuclei will behave similar to the Auger fit. So I don't want to talk about ultra energy cosmic rays from the sources in detail anymore, but I have like a few more minutes to just say that, of course, this is only like a cartoon picture of the real world, because we describe the sources not in this game, but in the propagation models, we just describe the interface to the sources. If you wanted to describe the sources, we typically use a different set of parameters, which you will show up there. For instance, you have like the luminosity per source, the size of this radiation zone, the Doppler factor of the source, if it's thrown towards us, the magnetic fields, again, the source distribution, a maximal energy or like an acceleration efficiency, things like that. What's ejected from the source, on the other hand, like comes naturally out there once you have a model for how the cosmic rays actually escape from the source. So at the end, you have a totally different set of parameters, but you can do the same games. I don't want to go through the details here because I don't have time. I just want to show you here, like this is, for instance, like descriptions of the same data by a source model, like a GRB model, in different versions of the Lorentz factor distributions, like a multi-collision model. And you can see that you can also produce the data like nearly perfectly apart from certain parameters. So that also works. And then if you look at the cosmogenic neutrino flux as an example, again, if you have the rigidity dependent model, which I showed you before, that is the gray curve here, versus the actual source model, it could be also higher in this region, because you actually have a certain fraction of protons in the system, which are naturally like postulated, because otherwise you cannot describe the physics of your source very well. So this means that it's not like guaranteed that you won't see anything there. That's cosmogenic neutrinos, like in a more sophisticated model. That would be the source neutrinos in comparison, like from these GRB models, which are below the current bound, but could be visible in IceCube Gen 2. So this is all I wanted to say at the end of this lecture. So today I was trying to, convince you a bit that cosmogenic neutrinos are an interesting subject and we need to study that, but it's not guaranteed that we would see anything at the highest energies from them. If you go back to my slides, I skipped this part last time for the AGN neutrinos. We could, I think, picture very well that these would be also ultra energy cosmic ray neutrino, ultra energy neutrino emitters, in the sense that, for instance, as you remember, the maximal neutrino energy will follow the proton energy. So if you have like actually ultra energy cosmic rays accelerated in AGN, for instance, the magnetic fields are low, you would also expect neutrinos peaking in these energy ranges. So maybe we will actually see AGN neutrinos there or some other kind of neutrinos as the foreground, and this will be like the background here. So this is not clear yet. This is why it's also interesting to pursue this avenue, like this radio detection of neutrinos. And maybe it's even richer than, like the low energy neutrinos, like low energy. From the current perspective, it's the high energy neutrinos we're talking about, like PeV, TeV neutrinos. But maybe EeV neutrinos are the business of your generation at some point, so we don't know that yet. And that was the main point apart from the TDEs actually for the third lecture. I would like to thank you for your attention.
Thank you, Walter. Other questions?
Yeah, just to add, all the slides are like available now, so you can also check the parts which I skipped if you wanted, and ask questions.
So actually, I have two questions, if I may. The first one is regarding the cosmic radio background, which should, in principle, also lead to production of secondary particles, cosmogenic particles, I guess, in ultra high energies. What are the predictions for fluxes from the cosmic radio background? Do you know if they have been done or if it's at all important?
So radio background, radio is like an EV, whatever, like 10 to the minus. What are the typical energies of radio emission? 10 to the minus 2?
Yeah, maybe I guess a couple of orders of magnitude lower than the CMB.
I mean, higher than the CMB probably, but lower, no more. I don't know. I don't recall what
the radio would be that way. So it would, I guess, would produce maybe a third peak.
Yeah, so it could produce, if they could produce a third peak, maybe at lower energies, but it would be probably like also like lower, I guess. So because otherwise, I mean, or it could be showing up somewhere here where, you know, you don't see like or have high sensitivity anymore.
Okay.
So I don't know if people really thought about this in that great detail, but probably it's not going to be a large contribution.
Okay.
Sorry?
So you would have to have cosmic rays at very high energies.
Yeah. Yeah.
I mean, we have to go back a little bit further.
The very end final tail of the spectrum, I guess. Yeah.
So when we have radio signals here, it's 10 to the minus 4 EV roughly, right? In this range or something like this. So this is like where you would expect, or like, yeah. But this is like probably not so different from the CMB energies, is it? Oh, so it would be here.
Yeah, yeah, exactly.
Okay. Yeah, that would mean that you have like higher energies, as you say, and then this would mean that, you know, like you have to accelerate cosmic rays to even higher energies. So it's kind of maybe not totally stupid, this idea, to put it like that, because we don't know how much they extend. But probably people have not thought about that or like propagated this too much because it sounds very aggressive.
Okay. And yeah, I have a second question. It was actually regarding this plot you were showing of this transition straight from pure proton to pure iron composition. If I'm not so if I understood correctly, that was this is the observed composition, right? At Auger or at so how can you explain? Of course, you cannot extrapolate this to the source's composition because of the photodisintegration.
Yeah.
So how can you explain this in terms if photodisintegration happens? If you have like a pure iron propagation, wouldn't you expect that part of it would photodisintegrate down to the lighter compositions?
Yeah, that's a very good question, and that's something which maybe some people also find kind of very suspicious. I mean, apart from the fact that if you have several sources contributing, you know, you would not expect this kind of like pure behavior. You know, and I think it's one of the major puzzles. Like, for instance, in one of the models I didn't show at the end, the GRB model, it's exactly the reason why sigma X max cannot be fitted very well, because whatever you do to realistic models, you will run into this problem. So some people say perhaps the explanation is that ultra high energy cosmic rays are actually driven by only like one or a few sources which are very nearby, or like a transient which happened or whatever. So maybe that resolves this puzzle, but yeah, maybe that's a little bit too far.
Okay, thank you.
Other questions? Oh,
my question is also related to this. So to explain the ultra high energy cosmic rays, we need for sure heavier elements, right? So do all the sources that are proposed have just like iron lying around to like accelerate it?
Yeah, I mean, this is also a very good question. I mean, the actual injection composition, I mean, there are like different discussions in the literature. Some people say, oh, yeah, if you need iron, that's very difficult because you cannot propagate it through the base of a jet. It would immediately disintegrate there, right? And then there are other proposals. Maybe it catches up it later also in the environment. there are people discussing, is it actually the composition you find in the environment, which you would like accelerate in the non-thermal particles, or is there maybe some kind of like enhancement factor depending on the mass of the element? So there are all sorts of like discussions around that. So it's not guaranteed that a priori what you find in the system. Like naively, we also had like models, for instance, where you would like disrupt like tidal disruption events of white dwarfs. White dwarfs may consist of like whatever carbon, oxygen, or I don't know. You put this as a composition, and you think that this will be the composition in your like jet, let's say. But this may be too naive at the end, because these kind of effects, like how you pick up elements, what kind of elements you accelerate or pick up easier, or things like that, may also affect this picture. Like especially in the AGN contexts, people have been coming up with that in the context of trying to explain how the galactic composition, or the composition you would expect in a galaxy, would translate into this kind of like picture. So it's like a dynamic subject, if you wanted, of research.
Okay, thank you.
Yeah, I have a question about the attenuation of gamma rays in TDEs. So I think you showed this one plot. Yeah, this one. And I think the cutoff is at around like 10 GeV, something like that. And I remember from Seyfert galaxies, for example, that you will have this kind of cutoff at like around 10 MeV. And I was wondering why there's such a large difference between the attenuation of gamma rays in TDEs and in like AGNs or Seyferts. Is that due to the different target photon spectrum?
Yeah, I mean, it depends on what you annihilate with, what the target the target is for the gamma annihilation, and what the temperatures are. And not only on the energy spectrum, but actually on the number density, which is sometimes misleading, because this is like not GeV per square centimeter in second, but 1 power of energy less.
Ah.
Okay, so one has to factor that in a way to see what the dominant target photon spectrum for the gamma process actually is, and then this would like lead to this kind of. So here we see typically, like if you go to the lowest energies, you would interact with the highest energy photons. I think that the X-rays are kind of efficient here, but in other cases they are not. So it depends a bit on, you know, what the. So I'm not even sure if that's true, or it's maybe dominated by that. But what the target photons are, which are dominating the gamma annihilation. So you can, from having the threshold, you know, like you have to produce 2 electron positron pair. If you write down the center of momentum equation, you can try to work out what the corresponding like target photon energy of that is. And I think I tried, and it was that, but I have to check it again. And for the corona, it may be different. They also have some, like in these models, they typically have like a high energy tail. And depending on how that translates into the number density, which is the relevant one for the annihilation, then you would have different gamma annihilation properties.
Okay, thank you.
Also on the TDEs, so I understood there is this triple structure with the disk, the outflow, and the jet.
Yeah.
Do we understand if the 3 events we have from 2019, if the jet is directed toward us, or if we're looking at it from a different perspective?
So for one event, there was like an evolving radio signal, which was 2019 DSG. And in that case, there were like jetted interpretations, like we were speculating about the jetted interpretation, even though, I mean, most FITs said that it's probably like a relativistic outflow, and the conditions for a jet are a little bit obscure. In the other systems, that was like pre-existing AGN systems. There were also like, I think in one case, a radio signal which was not evolving, so it was not considered interesting. So there was nothing really like super interesting there, which means that it's probably related to the pre-existing AGN. So that means if there is like a jet or so, then it was probably not pointing like in any direction of the observer, like maybe far away or something like this, or maybe it was a choke jet or something like this. So this could also happen, like a jet which is absorbed in the surrounding material. So the jetted interpretation, also not all TDEs emit jets. So they are now like new considerations, like there was a jetted TDE last year, which is called AT2022 CMC. I don't know if you've heard about that. And from that paper, they derived that about 1% of all TDEs have jets, like not necessarily in our direction, but in any sort of direction. But it's still interesting, like we did the diffuse flux computation, that the 1% of all TDEs having jets is kind of consistent with the 1% of all TDEs emitting neutrinos. Okay, so you can speculate what that means, but perhaps, I mean, it's actually off-axis jets, which are the accelerators of the neutrinos or of the protons, which escape then in our calorimeter, in this calorimeter, producing the neutrinos in an isotropic system. So the neutrino emission is most likely isotropic from the observations, even though that leads to problems with energetics, because you really need a lot of power in these non-thermal protons then to really see the neutrinos. But the jets is like, I would say, getting more speculative.
Okay.
After this, yeah.
Okay, thank you.
Okay, I would, did you have a question as well? Oh, so yeah, maybe if there are more questions, I think you are also here for the lunch break. Maybe we can talk about this. So let's thank Walter again for today and also for the whole lecture series. I mean, you covered a lot of ground, yeah? So there's a lot of interesting information also for you to think about for future projects. So thanks a lot. Yeah?
Okay.